Hello. In this class, let's talk about microcontrollers. We're gonna learn about what are microcontrollers, the applications in real-life problems, and the internal architecture. Before we continue, remember to subscribe in our channel and like the video, to help us keep growing. The technology of using solid-state components in electronics has experienced an unprecedented technological revolution in the entire history of electronic devices. Integrated circuits have gone a long way, and nowadays, there are full-fledged computers on a single chip, microcontrollers. The idea is simple, a computer reduced to a very small size. Additionally, it is cheap and encapsulated in a chip. A microcontroller contains a clock generator, ROM, flash, and RAM memories, input and output interfaces, processor, signal converters, and other components depending on the model. Microcontrollers are used in specific systems or embedded applications, such as toys, remote controls, appliances, and industrial machines. In 1960, engineers from a Japanese company grew up with a goal to order Intel to develop integrated circuits for calculators. On the spot, the engineer from Intel had the idea to develop an integrated circuit, such that the very work of the integrated circuit would be described by a program that would be written to the chip itself. It gave the world the first microprocessor. From now on, Intel realized what a brilliant child it had given birth to. It bought up its license and patent for the product and introduced it to the market in the form of the 4004, with 4-bit words at a speed of 6,000 instructions per second. The following year there was an 8008, with 8-bit words, which can look 16 kilobits memory, work at a speed of 300,000 instructions per second, and operates 45 instructions. Following this, additional companies acknowledged the promise of microprocessors and embarked on their own development endeavors, resulting in a diverse array of architectures and functionalities. Each manufacturer has crafted its unique architectural blueprint, each with its own strengths and weaknesses. This architecture encompasses the organization of fundamental components, the instruction set, and the execution process. Nevertheless, there are core elements inherent to microprocessors across all designs: the arithmetic logic unit, ALU, the register array, the control unit, and the instruction decoder. This is a representation of the components of the CPU. The arithmetic logic unit, ALU, is responsible for performing basic arithmetic operations, additions, multiplications, shifts, etc., and logical operations, and, or, not, XOR, etc., based on data obtained from the register array. The ALU is managed by the control unit. The instruction decoder, while technically considered part of the ALU, is often defined separately due to its significant function. The microprocessor operates by executing instructions stored in memory, typically in binary format. The decoder sequentially translates each stored instruction into a format understandable by the ALU. To enable the ALU to carry out program instructions, it requires temporary storage of data and addresses for processing. This storage function is fulfilled by a group of registers referred to as the register array. Once the instruction decoder finishes interpreting instructions, the control unit steps in by issuing control signals and timing signals. These signals facilitate the transfer of data into or out of the microprocessor. Furthermore, the control unit ensures synchronization in the execution of instructions. The microprocessor is the heart of any computational system. Yet, for it to function effectively and deliver meaningful outputs, it relies on an array of peripherals or functional components. These include RAM, program memory, analog-to-digital converters, ADCs, oscillators, interfaces, and various other elements. Together, these peripherals enhance the capabilities of the microprocessor and enable it to perform a wide range of tasks. A microcontroller is composed of logic circuits, special function registers, SFR, input-output ports, I/O, memory units, central processing unit, CPU, buses, oscillator, timers, counters. Microcontrollers function on the principles of logic circuits or logic gates. These gates are composed of interconnected transistors, diodes, resistors, and capacitors, enabling them to perform binary and logical operations using the numbers 0 and 1. The fundamental logic gates include AND, OR, NOT, and XOR gates. By utilizing these gates, it's possible to define additional gates and arrange them in various configurations to achieve specific desired outcomes. And gates have two or more inputs and a single output. the output of an AND gate will be at logical level 1 only when all of its inputs are at logical level 1. If any input is at logical level 0, the output will be at logical level 0. Below is a truth table illustrating the binary results. OR gates, similar to AND gates, have 2 or more inputs and a single output. The output of an OR gate will be at logical level 1 whenever any of its inputs are at logical level 1. If all inputs are at logical level 0, the output will be at logical level 0. Here's a truth table demonstrating the behavior. NOT gates, also known as inverters, have only one input and one output. The output of a NOT gate is the inverse of its input. If the input is at logical level 1, the output will be at logical level 0, and vice versa. Here's a truth table demonstrating the behavior. XOR gates, or exclusive OR gates, can indeed be considered a combination of the previous gates. They produce a logical level 1 output only when their inputs have different logical levels. In other words, if one input is at logical level 0 and the other is at logical level 1, the output will be at logical level 1. However, if both inputs are at the same logical level, either both 0 or both 1, the output will be at logical level 0. Below is a truth table illustrating the behavior. The output of an XOR gate can indeed be confusing depending on the number of inputs. When the gate is only 2 inputs, the output will be at logical level 1 only if the inputs have different logical levels. However, if the XOR gate has more than 2 inputs, the output will be at logical level 1 only if the number of logical level 1 inputs is odd. For example, in a 3-input XOR gate, if the inputs are 100, an odd number of level 1 inputs, the output will be 1. If the inputs are 110, an even number of level 1 inputs, the output will be 0. This principle holds true for XOR gates with any number of inputs. Registers are electronic devices designed to store the logical levels of bits. They share similarities with memories, but with a key distinction: while memories solely store bits, registers actively control certain operations. Within a microcontroller, there exists a multitude of registers, with some components being governed by dozens of them. Due to the extensive variety of registers within the microcontroller, they are identified by specific names. For instance, the 8MEGA128 microcontroller features a register known as UCSRNA, USART Control and Status Register A. This register is employed to both read states and configure a module within the 8MEGA128 microcontroller known as USART. Special Function Registers, SFRs. Microcontrollers rely on interfacing with the external environment to execute their tasks. This interaction is facilitated through registers linked to the microcontroller's pins, referred to as input and output ports. As these registers can be manipulated by software, designers have the flexibility to adjust both input and output functionalities, including real-time value modifications. I/O ports. In the specifications of a microcontroller, a crucial aspect is the maximum current tolerance of its pins. Typically, each pin can handle currents ranging from 5 to 25 milliamperes. It's important to recognize that this maximum current is distributed among all the pins when evaluating a microcontroller's technical specifications. Consequently, as the number of pins on the controller increases, the maximum current that each pin can bear decreases. The I/O port pins are managed by Special Function Registers, SFRs. These pins generally operate at logic levels of approximately 0V or 5V. For instance, when a register sets bit 1 to an I/O port pin, the voltage at that pin rises to 5V, configuring it as an input. Conversely, if the register sets bit 0 to the pin, the voltage drops to 0V, configuring it as an output. Memory. Microcontrollers require various types of memory for data storage. Each memory position is accessed by a unique memory address, enabling reading or writing of its contents. Manufacturers employ different types of memory based on their design requirements. Here are the most common types of memories. ROM, read-only memory reserved for permanent programs, allowing only reading. OTP-ROM, one-time programmable ROM designed for writing a program just once. It's where the designer loads their control program to execute the desired task. Once written, it cannot be modified, requiring a new chip for changes. UV-EPROM, ultraviolet erasable programmable ROM, offers more flexibility as data can be erased using ultraviolet light, enabling chip reuse. Flash, highly flexible, allowing electrical writing and erasure multiple times. RAM, random access memory essential for temporary storage in almost all microcontroller processes. It's volatile, meaning its data is lost when power is turned off. EEPROM, electrically erasable programmable ROM, frequently used for storing values generated during microcontroller operation, retaining data even when power is turned off. It can be electrically erased for updates. CPU. The Central Processing Unit, CPU, serves as the microcontroller's brain, overseeing and managing all internal processes. It typically comprises an instruction decoder, an arithmetic logic unit, and an accumulator, with potential additional units depending on the manufacturer. The instruction decoder reads and interprets program instructions, triggering actions in other parts of the circuit. Meanwhile, the arithmetic logic unit executes logical and mathematical operations. The number of instructions varies across microcontroller families, defining their capabilities. The accumulator, a special function register, works in tandem with the arithmetic logic unit. It stores data for manipulation during operations and retains results for subsequent processes. The accumulator features a special function register known as status, which stores information about the data held within the accumulator. Bus. To streamline memory access and data transfer between different units within the microcontroller, buses are employed. These are pathways or lines whose quantity is determined by the data word size or the maximum number of addresses that require access. There are two primary types, the address bus and the data bus. The address bus serves as the channel through which the CPU dispatches the memory address for reading or writing. Meanwhile, the data bus interconnects all internal circuits of the microcontroller and varies in size based on the number of bits to be accessed or transmitted at once. Serial interfaces. While microcontrollers facilitate parallel communication between their I/O ports and peripherals, long-distance parallel transmission can be costly and subject to synchronization constraints. Hence, most modern microcontrollers integrate built-in serial communication systems. Here are the commonly utilized ones. I2C, inter-integrated circuit employed for short-distance communication, typically within the same board where the microcontroller and peripherals reside. Communication utilizes a pair of conductors, one for data transfer and the other for the clock signal, ensuring synchronous operation. SPI, Serial Peripheral Interface Bus, utilizes up to 4 conductors to enable full duplex communication. It employs one conductor each for sending and receiving data simultaneously, one for the clock signal, and another for device selection. Consequently, SPI boasts a higher communication speed compared to I2C. UART, Universal Asynchronous Receiver/Transmitter, operates with just one conductor for asynchronous communication. In full duplex communication between two devices, both can transmit and receive data simultaneously. Oscillator. In the realm of microcontrollers, oscillators serve a critical function in providing the timing signals necessary for various operations. They generate clock signals that synchronize the activities within the microcontroller, ensuring proper coordination and timing accuracy. Analog to digital converter, ADC. Microcontrollers frequently interface with external signals, many of which are analog in nature. However, the microcontroller operates primarily with digital signals. To bridge this gap, analog to digital converters, ADCs, come into play. These components receive analog voltage signals at their input pins, convert them into digital representations, and transmit the resulting digital data to the CPU for processing. Internal architecture. Microcontrollers employ distinct internal architectures to manage program instructions and data. Two prominent architectures are the Harvard architecture and the von Neumann architecture. In the von Neumann architecture, both program instructions and data are stored within the same memory space. This unified memory structure leads to a single bus system, which the CPU uses to fetch instructions or read/write data. However, since these processes cannot occur simultaneously, the bus may become congested, resulting in slower communication. Conversely, the Harvard architecture features separate buses dedicated to distinct functions and utilizes 2 distinct memory units, one for storing program instructions and another for data. This setup enables simultaneous fetching of instructions by the CPU from one memory while accessing data from another. By segregating the instruction and data pathways, the Harvard architecture enhances communication efficiency. Additionally, the 2 buses may have varying numbers of lines to accommodate their specific functions. Applications of microcontrollers. In today's industrial landscape, electronic integration is pervasive across a wide array of products, spanning air, land, and sea vehicles, as well as household appliances. Microcontrollers serve as indispensable solutions for achieving compact, cost-effective, and programmable computational capabilities in such applications. However, selecting the appropriate microcontroller entails careful consideration of factors such as input and output requirements, serial communication needs, the necessity for A/D converters, stability, and processing speed, among others. Once project specifications are delineated, the choice of the suitable microcontroller from the diverse range of offerings becomes paramount. Factors such as the price per unit and the required quantity of units also influence the selection process. Among the myriad microcontroller families available, the following are particularly prominent: Atmel 8-bit AVR, Cypress Semiconductor PSoC1 Programmable System on Chip, Freescale Semiconductor Motorola MC6800, Infineon Technologies Tricore, TCXXXX, MCU, Microchip Technology PIC16 MCU, Silicon Laboratories C8051F33X, ST Microelectronics STM32, and Texas Instruments MSP430. Microcontrollers find application across a multitude of products, including aircraft electronics, embedded vehicle electronics encompassing functions such as brakes, steering, carburation, stability control, shock absorbers, multimedia, and device management, industrial process control systems overseeing tasks like flow measurement, electricity metering, sensor monitoring, motor control, robotics, thermostat regulation, and access panel management, agricultural sectors like poultry and swine farming, entertainment devices including toys, video games, consoles, and music players, telecommunication infrastructure such as routers, switches, cell phones, tablets, watches, GPS devices, Bluetooth peripherals, and Wi-Fi connectivity solutions, healthcare and aesthetic applications such as blood pressure monitors, pacemakers, and various medical equipment, home automation systems, domotics, facilitating smart control of household functions, household appliances ranging from kitchen appliances to laundry machines. Is this for this class? Let in the comments if you have any doubts. See you soon. Bye-bye.